Hello everyone, I am Amshi from ECD section. My AAT Tech Talk topic is about the diffusion and heat equations. This topic discusses numerical solution to the heat, conduction and diffusion equation, discuss the physical problems and properties, examine the equations, approximate solutions using a finite difference equation, consider numerical stability examples. By the end of this, you will understand the heat conduction diffusion equation, understand how to approximate partial differential equations using finite difference equation, set up solutions in one spatial dimension, understand the implementation of insulated boundaries. Suppose you have a metal bar in contact with a body at 100 degrees Celsius. The bar is insulated over time. The entire length of the bar will be at 100 degrees Celsius. At time t is equal to 0, one end of the bar is brought in contact with the heat sink at 0 degrees Celsius. At the end closest to the heat sink, the bar will cool rapidly. However, the cooling is not uniform. Over time, however, the temperature will drop linearly from 100 degrees Celsius to 0 degrees Celsius across the bar. The equation that describes the change in temperature over time is given by the partial differential equation. It is 1 dou by x 1 by k dou by dou t u is equal to square u, where u of x comma t is a real valued function of space and time k greater than 0 is the thermal diffusivity coefficient, heat conduction diffusion. Applications of the heat conduction diffusion equation include heat equation, Fick's law of diffusion, thermal diffusivity in polymers. Rate of change of proportional to concavity. In one dimension, what does this equation mean? Dou by dou t u is equal to k dou square u by dou x square. Recall, we assume that k greater than 0, if the function mu is concave up at x comma t, the rate of change of u over time will be positive. That is, it will become less concave up. If the function u is concave down x comma t, the rate of change of mu over time will be negative. That is, it will become less concave up. We can see this visually. Dou by dou t u is equal to k dou square u by dou x square. If the function mu is concave up at x comma t, the rate of change of mu over time will be positive. Consider heat conduction problem. A bar initially at 5 degrees Celsius with one end touching a heat sink also at 5 degrees Celsius. At time t is equal to 0, the other end is placed in contact with a heat source at 80 degrees Celsius. A plot of the temperature over time across the bar is given by this solution. The end placed in contact with 80 degrees Celsius heats up faster than points closer to the heat sink. As the concavity becomes smaller, the rate of change also gets smaller. Approximating partial derivatives. Recall our approximations of the partial derivatives. Mu of x is equal to mu x of mu of x plus h minus mu of x minus h by 2h. Mu of x is equal to mu of x plus h minus 2 mu of x plus mu of x minus h by h square. In this case, however, we are dealing with partial derivatives. If you recall the definition of the partial derivative, we focus on the variable and leave the other variable constants. Dou by dou x mu of x comma t is equal to limit h to 0 mu of x plus h comma t minus x comma t by h. Dou by dou t mu of x comma t is equal to limit mu of x comma t plus delta t minus mu of x comma t by delta t. To ensure clarity, h is used to indicate small steps in space, delta t is used to indicate a small step in time. The obvious extension is to define dou by dou x u of x comma t is equal to u of x plus h comma t minus u of x comma t. Dou by dou t mu of x comma t is equal to mu of x comma t plus delta r minus mu of x comma t delta t. The next step is to approximate the concavity. Mu of x comma t plus delta r equal to u x comma t plus delta r into k dou square u by dou x square. We will use our second order formula. Dou square by dou x square u of x comma t is equal to u of x plus h comma t minus 2u x comma t plus u of x minus h comma t by h square. To get u of x comma t plus delta t equal to u of x comma t plus delta t k into u of x plus h comma t minus 2u x comma t plus u x minus h comma t by h square. U of x comma t plus k delta t by h square mu x plus h comma t minus 2u into x comma t plus u into x minus h comma t. There is only small interesting issue. What happens if the coefficient u into x comma t plus delta t is equal to u x comma t plus k delta t by square, u into x plus h comma t minus 2u x comma t plus u x minus h comma t is very large. It should be obvious. However, we will be approximating these at discrete points. Mu k comma l plus 1 is equal to mu k comma l plus k delta t by h square mu k plus 1l minus 2 mu k comma l plus mu k minus 1l. Initial and boundary conditions. For a first order ODE, we require a single initial condition. Y of t is equal to f of t comma y of t. Y of t1 is equal to y1. Initial and boundary conditions. For a second order ODE, we require either two initial conditions. Y of t is equal to f of t comma y into t comma y of t. y of t1 is equal to y1, y of t1 is equal to y1, or a boundary condition c1 y of x plus c2 y of x plus c3 y of x is equal to g of x, y of a is equal to ya, y of b is equal to yb. For the heat conduction diffusion equation, 1 by k into dou by dou t into u equal to square u, we have the first order partial derivative with respect to time, a second order partial derivative with respect to space. We require for each space coordinate, we require an initial condition for the time. For each time coordinate, we require boundary condition for the space. In this case, we will require an initial value for each space coordinate, keeping in the spirit of one dimension. If we were monitoring the progress of the temperature of a bar, we would know the initial temperature at each point of the bar at time t is equal to t1. If we were monitoring the diffusion of a gas, we would have to know the initial concentration of the gas. Okay, thank you.